Okay, now we'll see how to draw influence line diagrams forces in the Warren Truss. Draw influence line diagrams for forces in the members of Warren Truss. Similar to the Pratt truss, he proposed N-type truss. Warren proposed a truss without vertical members, and that truss is named after him. Members of Warren Truss. Warren Truss means a truss without vertical members. Shown in figure. A truss without vertical members. Now you see, now we'll try to draw influence line diagrams for the forces in the members of Warren Truss. Assume that this is one such Warren Truss. Now this is called Warren Truss. It doesn't have any vertical members, only diagonal members. Let us say lower chord members, let us name them L1, L2, L3, L4, L5. Upper chord members, let us say U1, U2, U3, U4. We have 4 panels at 3 meters. So total length is say 12 meters. This one, you assume that these angles are 60 degrees. That means the height of the truss will be 3 sin 60. You will get 2.59 meters. So, so much you will get. This is now the ground. Let us say for any position the reactions are V1, V2. The reactions are V1, V2. Suffer some loading, let us say. We are interested all the top chord member we have drawn in the Pratt truss, diagonal member we have seen. Now what is left out is the bottom chord member. Now we will draw for this one bottom chord member. So L3, L4 you want to take say. Then we have to cut it by a section 1, 1. This is a section 1, 1. Now the disturbed panel is L3, L4. In the disturbed panel we should not keep the load, keep it somewhere here. Between L1 to L2 to L3, anywhere you can keep it, so that no part of the load goes to the other side of the cross girder. If it goes other side of the cross girder, some part of the load acts also, it will also act at the joint. You have to deal with that part load also, you have to take it and find moments, etc. So that's why you will keep it between L1 to L3. Okay. Now this is the process. We are taking now ILD for F, L3, L4. Last class in the Pratt truss we have seen let the load is between L1 and L3. Now look left side, draw expression. Now second case, load is on the right side. Now see left side, then find moment. That much story in the exam we should not take it. Now you understood the process because we have taken 4 examples. Now let us see. In the exam, in the rough work, what you have to have only this much. Keep the load here, cut it, look right side. Now we wanted L3, L4. These two unwanted members are meeting at U3. Take moments of all force about U3. So travel from tail to the head towards U3. This is giving anti-clockwise. So this you should give clockwise like this. F, L3, L4 gives clockwise moment about U3. So this distance you will get 4.5 meters. This is around 3 plus 6 plus 1.5. So 7.5 meters like this. So in the exam, in your rough work, only this equation should be there. Left side, right side, you will not say. Then take moments of all forces about U3 is equal to 0. That means we are keeping load on the left side, you cut it by 1, look right side, and this is the equation. So clockwise positive, anti-clockwise negative. So minus V2 into 4.5 plus FL3 L4 into 2.59. Clockwise is 2.59, height is so much. So you will get FL3 L4 is equal to 1.74 V2. Arrow mark away from the joint, so tension. So draw ILD. We are drawing ILDs only. We don't have to draw again their ILD like that. So this is your ILD for F, L3, L4. See tension 1.74 V2 means you have to draw above reference line 1.74 V2, it will go something like this. This ordinate is 1.74 V2, nothing but 1.74. But this expression is valid only when the load is between L1 and L3. That means up to here only it is valid. Also that point up to here. Now this is a construction line like this. We'll cut it off. Okay. Next. Now we'll keep load here. Unit load here, cut here, look left side. Now this produces clockwise, V1 into 7.5 clockwise. Now this should produce anti-clockwise. And this arrow mark now you have to keep it here. We have to keep the arrow mark here. This is FL3, L4. Okay. Now this is anti-clockwise, clockwise. You see now also it is tension. Okay, let it be tension. Now take again same point, moments of all forces about U3 is equal to 0. Clockwise positive, anti-clockwise negative. So plus V1 into 7.5 minus F L3 L4 into 2.59. So you will get FL3 L4 is equal to 2.89 V1 tension. So draw ILD for 2.89 V1 and consider between L4 and L5 only. Because you have taken moment center about U3, those two lines intersect about this point. So it will go now something like this. This is now 2.89 means extended line will go something like this. So they will intersect somewhere here. This is 2.89 V1, nothing but 2.89. So where valid only up to here. This is also positive. See 2.89 by 4. For 4 panels it is 2.89. One panel how much is the ordinate? So you will get 0.7, 0.73. Next here, for 4 panels 1.74, for 2 panels 1.74 by 2. You will get 0.87, 0.87, 0.73. Now the disturbed panel has no choice, it must be a straight line. Already up to here we have drawn, up to here we have drawn, so connect it. This is again plus, like this. Now this is again tension positive, compression negative, like this. Now you see this diagram tells you that for all positions of unit load, force in the member L3, L4 everywhere tension only. When the load comes to L3, his influence on L3, L4 is 87%. 0.87 into say 10 kilonewton load is moving. So 10 into 8.87. If the load comes to L4, his influence on of L3, L4 is again tension, but his influence on only 73%. So 10 into 0.73, that means 7.3 kilonewton is the tensile force in this member. That means wherever load is there, force in the member is tension only. Such members we call them as pure tension members or simply tension members. Okay. Now because there is no way they will buckle, buckling problem is not there, unwanted bending is not there when we are pulling them. So you can have slender sections also. So slenderness ratio you can go up to 400. 400 means compression members 180 I told you. Tension members now it is 400. That means when compared with the length, cross section can be less. So it looks thinner member. Slenderness ratio more implies that it is a more slender member. Slenderness ratio less means it is a bulky member. That is the implied meaning of that slenderness ratio. So why we go for 400? Why to limit 400? Why can't it be 1000? Supposing that if the slenderness ratio is 1000, then it becomes so thin. It can take load, but cross section will be so small that due to self weight itself, it will sag. Like a cable, it will behave. In a truss, even tension members also, that straight configuration should not be lost. If straight configuration is gone and it behaves like a cable, let us say, then you cannot call it as a truss member. If you see towers, transmission towers, one tower is here at 1 kilometer or so, one more tower will be there, and cables they will sag. However hard you pull the cable, it will still sag due to its self weight. So that type of problems will come. Sagging will take place due to its own weight. We don't want that to happen. That is the reason why slenderness ratio is limited to only 400 for tension members. Okay. Supposing that this is a pure tension member, when the loads are moving, there is no way it will be under compression, it is only tension member. But when wind loads are acting, wind loads means if they act like this again tension, but wind loads can act this way also. So when wind loads are acting like this, sometimes the roof covering material is there, say, and the roof covering material will be blown off. That means it is pushed up like that. Such cases there will be due to wind load some compression will develop. but that compression is so small that the instead of 400 you can go up to 350 also, because compression force is very less, so slenderness ratio you can go up to 350. Or earthquake load, suppose two columns are there here, base isolators are there, then the compressive forces that transfer here is very less. If they are not there, the earthquake shakes the footing, let us say, then horizontally it pushes, then that force will be transferred to the column. Column will in turn transfer the load to the bottom members. Such cases, the for the bottom members may be under compression. So due to earthquake load or due to wind loads, they can be under compression. Under such cases where there is a possibility of compression due to wind load or earthquake load, you limit the slenderness ratio to 350, not 400, slightly less value. Okay, so these are the conclusions. For all positions of moving load, force in the member L3, L4 is tensile. Such members are called pure tension members, or say simply tension members. Maximum slenderness ratio, we call it as lambda. Effective length by corresponding radius of gyration, either Lxx by Rxx or Lyy by Ryy, should never exceed 400. Okay, that is the codal provision. This is as per IS 800/2007. This is the slenderness ratio definition. Strength of material sirs might have told you. Effective length of a column by corresponding radius of gyration gives you the slenderness ratio. If Lx6 and Lyy are same, then you will write effective length by minimum radius of gyration. It is a particular case. If Lx6 and Lyy are same, then you can write effective length by minimum radius of gyration. If two lengths in two different directions are different, then effective length by corresponding radius of gyration is the correct definition for slenderness ratio. Okay, it should not exceed 400. We will discuss how that slenderness ratio looks like, etc. in the again in the steel structures. So second point is, why should it be like that? If lambda exceeds 400, then tension member behaves like a cable and sags due to its self weight and straight configuration. And straight configuration of member will be lost. So one paper they asked this as assertion reasoning type. For a tension member, slenderness ratio should not exceed 400. Assertion. First, you have to confirm whether it is correct or wrong. Next, if it exceeds 400, the reason. The tension member sags due to its self weight. So, assertion, reason are correct, and reason is the correct explanation for the assertion why we are having uh, not more than 400. Okay. Supposing that such tension members, if they are subjected to reversal of stresses, third point, if a tension member is subjected to reversal of stress due to wind load or earthquake load. WL means wind load, EL means earthquake load. Reversal of stress due to wind load or earthquake load, maximum slenderness ratio lambda should not exceed 350. Okay, this is what is the provision. Again, the design of steel structures, we write all these points, but all will write them at one point, at one location. Now you see, these members can be subjected to reversal of stress due to wind load or earthquake load only. But these members are subjected to reversal of stresses due to live load. So for these cases, live load reversal means very high stress, compressive stress will develop. So slenderness ratio for them is 180. This, if there is a compression due to wind or earthquake, slenderness ratio slightly reduced to 350 instead of 400. So that reversal of stress due to what? Depending on that, we have the uh, values of the slenderness ratios. Next. Now, we'll see how to draw ILD for FU3, L3. Now, second one is ILD for FU3, L3. Again, here you see cut it by 1, load is here, look right side. So, there is an upward force. To balance an upward force, here the arrow mark must be downward. This one, FU3, L3. This angle we know 60 degrees. So FU3, L3 is sin 60 minus plus V2 must be 0 when the load is here. Directly write that expression. We must be able to write that one. Cut, load is left, look right side, sigma y 0. Upward force is positive, downward force is negative. Plus V2 minus FU3, L3 sin 60. So you will get FU3, L3 is equal to 1.15 V2. Arrow mark is away from the joint, so tension. So draw ILD for 1.15 V2 and consider between L1 and L3 only, like this. ILD for FU3, L3. Tension means above reference line we have to show 1.15 V2 means we have to show like this. 1.15 V2. V2 influence is only 1. So this way. Okay. Now out of this up to here only it is valid. So this is plus. Now this is not valid. So for 4 panels 1.15, 2 panels, this is 1.15 by 2. Next, keep the load between L4 L5 somewhere here, cut it, look left side. Now, why look left side is, if you can see right side also, but 1 minus V2 again becomes V1 only. So directly you can see left side and get the same expression. So cut here, look left side. So this is upward. To balance it, it has to be now downward. Because this arrow mark, they will not have any vertical component. So it has to be downward. F, U3, L3. Now if you write sigma y0, plus V1 minus F U3 L3 sin 60. So you will get F U3 L3 is equal to 1.15 V1. Arrow mark is towards the joint, so compression. So 1.15 V1 means it will go here like this. Below reference line, nothing but 1.15. So it will go something like this. Like this. This 1.15 V1. Out of this, load is between L4 L5 only, that expression is valid. So up to here only have to consider. See here, for 4 panels 1.15, one panel, this will become 1.15 by 4. Now you see, after that left out panel is the disturbed panel. So up to here we have drawn, already we have drawn up to here. So it will go now like this, plus minus. It has to be straight line only. So what this diagram tells you is this U3 L3 member is subjected to reversal of stress due to live load. When the load is moving from L1 to L2 to L3, the tensile force in this member increases. Once load crosses L3, the tensile force decreases to 0 somewhere in between. Once it comes to L4, force in the member becomes compressive and its magnitude is maximum. And the load is moving from L4 to L5, his influence on U3 L3 gradually reduces to 0. So this is the influence. In a day, 1000 times trains move, 1000 times it is pulled and pushed. So reversal of stress is for 1000 times. So accordingly, fatigue we have to take into account when you are designing this member. So this is ILD for FU3 L3. They can ask you to stop at this level because you have only 1 minute time in the exam. So once one line if you draw up to here, you are able to draw, say. Then sometimes they ask you only one thing. What is the ordinate of FU3L3 at joint L3? That's all. 1.15 by 2 you find it, say. Then stop the work. Entire thing you don't have to draw. Another way is 4 diagrams they give you and up to here only one option matches, say. Then tick it. If two options are similar, 1.15 by 2, another also 1.15 by 2, then you have to exceed. Then it should reverse its direction, means it should go like this. Okay. It should go gradually only. Sudden jump should not be there. It cannot suddenly from 1.152 to 1.15 by 4 cannot vertically jump. So it should be when the load is moving, it will move like that. It changes like this. Sudden change in variation in the force not possible because load is moving on the rail, not on the truss. So now another way of asking is they give you the truss, they give you the ALD, ordinate also they give, positive area how much, negative area how much they will give you. Due to dead load and live load, what is the maximum force that you may get? That they can ask. Such cases, what is the force in the member if dead load is given? Whether we like it or not, dead load must be kept full length because dead load you cannot remove. Dead load is because of what? Self weight of truss, sleeper weight, rail weight, stringer beams weight. That's all including self weight of the truss bridge, let us say 10 kilonewtons per meter. You like it or not, it will be there full span. So we have to keep full span. Then live load is there, say. Then live load, if you want to get maximum tensile force, you keep it in this zone AB. That live load you have the choice to move up, forward, backward. If the live load is on the span AB, wherever it cuts the uh, horizontal line, then you will get maximum tensile force. If the live load is between BC, let us say, then you will get maximum compressive force. That means live load should not be here and engine should go beyond the support and last compartment onwards it should be there here like this. Okay, like that. Dead load always we have to keep in full length. Live load you have the choice. Including in addition to live load, if point load is there, say, then point load you have to keep at the L3 or L4, whatever may be the case. So when UDL is there, how to manage, point load is there, how to manage we know. Then judiciously judge and accordingly adjust the loads. Now let us see how a numerical can come. If the warrant truss is subjected to a dead load of 10 kilonewtons per meter and a moving live load of 20 kilonewtons per meter, maximum tensile force in the member U3L3 is. Now see, if like that is given, dead load you must keep it full length like this. So because dead load you have no choice, you cannot adjust. It is fixed in position. This is a dead load of 10 kilonewtons per meter. And moving UDL length is not given. That means the UDL is always longer than the span. That means live load will should be kept up to B like this. This value is now 20 kilonewtons per meter. So that means you should know where B is. That means from similar triangles you will get it. Location of B. From similar triangles. This distance you take it as a x. This will be 3 minus x. So x by 1.15 by 2, 3 minus x by 1.15 by 4. You can get what x is. X by 1.15 by 2 must be equal to 3 minus x by 1.15 by 4. So x you will get from this one 2 meters. That means from here to B is 3 plus 3 plus 3 plus 2. So up to here it is 8 meters. Then this is here 1 meter plus 3 meters. So you will get 4 meters for the remaining length. Now to get maximum tension, keep DL and LL as shown in figure. Now you see F U3 L3. Now DL plus L up to AB span you have dead load plus live load. So 10 plus 20 into positive area, half base is 8 meters. That means from here to here is 8 meters. This is 1.15 by 2. Half base into height. This is dead load plus live load. This is positive area of ILD plus dead load. The other portion only dead load 10 kilonewton into negative area minus half base is 4 meters, height is 1.15 by 4. This is dead load. This is negative area of ILD. Negative area of ILD means this triangle. From here to here, this is 4 meters. This height is 1.15 by 4. Height we know. This one. So half base into height. You will get negative area of ILD into only 10 you have to write. So whether we like it or not, when dead load is there, that negative area also you have to take it and subtract. Not full only this you cannot take it. Dead load must be kept. So you will get around 63.25. Okay. Now these are the fundamentals about the influence line diagrams for the forces in the truss members. Now let us see some more numericals on this one. Now ILD for force in the member CG. 4 options they will give it, you have to take the correct one. This point let us say A, B, C, D, E, F, G, H. Once it is asked for a 2 marks question in GATE, 4 diagrams they have given, you must select the correct one. How to select? ILD for FCG means CG member you see 1, 2, 3, 2 are in line, force in the third member is 0. That earlier in the prot-truss I have told you. In the prot-truss, this joint configuration was at top. That means unit load will never come to the top joints at all. But here loads are moving on the lower chord members. So when the loads are moving on the lower chord member and joint configuration or the member configuration is at the lower chord itself, then what happens is when the load is moving, when the load comes to C, it can come to C, then entire load has to be taken by CG only. But that possibility was not there in the Pratt truss because load is moving here, but this configuration was at top. Load will not go to the top. So for all positions of moving load, you got a straight line in the Pratt truss. But whereas here, the member configuration is at the bottom joint and also load is moving there. So we have to take it now like this. Such cases where the loading is moving on the bottom chord and three members, two members collinear, third member is also at that point bottom chord only, then this is the process. For such problems only I told you when load is moving on the rail, not on the truss. So when the load is moving on the rail, how the load gets transferred from the rail to the cross girders? We should have clear picture, otherwise this type of problems you cannot solve. Now you see, when the load is here, part of the load goes to A, remaining goes to B, but nothing goes to C because it's like a simply supported rail is the assumption. So when the load is between anywhere between A and B, now force in member CG means here nothing came. So 1, 2, 3, 2 are in line, third must be 0. So like this. For the all positions between A and B, influence line diagram is simply straight line. Now you see, when the load is here, part of the load comes here, remaining goes here, but nothing goes to C. So that means between D to E, force in the member CG is 0 only because no load is coming here. So this is over. But when the load is exactly here, that means there is a rail here, there is a cross girder. When the load is on the rail exactly at the cross girder itself, entire load is taken by the cross girder only and cross girder will pull the joint. Okay, when the load is here on the rail, that load directly transfers to the cross girder. Cross girder in turn will pull the truss joint. So this is one down, that means this will be one up. That means force in member is tension. That means influence of 1 on the CG is 1. So the influence only we have to draw here. So its influence is 1 now. Now having found so many points, now we can join this panel we have written, this is over. In this panel, here it is 0, here it is 1. Then how to join? Straight line only. In this panel, here it is 0, here it is 1. Within the panel, ILD must be straight line. So plus like this. This is ILD for F CG. This is the process. That's why it is a 2 marks question. When unit load is between A and B, force in the member CG is equal to 0. Why? This is the configuration. Nothing comes to this member. Then same thing, when unit load is between D and E, unit load is between D and E. Same process, force in the member CG is 0. Then when unit load is exactly at C, force in the member CG is 1, tension. This configuration is like this. 1 down here, force in the member CG up, 1 up, arrow mark is away from the joint. So tension. So draw ALD as shown in figure. Now how this will be correct? Let us see. If at all load is exactly on this panel somewhere here, say, can be there, exactly center. So this cross girder takes zero point 0.5, this cross girder takes 0.5. That means one cross girder take zero point 0.5 down, then force in the member is zero point 0.5. That is reflecting here, you see. This is zero point 0.5. So 1 into zero point 0.5 is the cross girder force. Cross girder force again transfers to the member CG. So zero point 0.5 you will get. That means that is correct. What we have done is correct. So that's what force in member CG. Now let us see one more problem. Consider the following statements for n girder shown in figure. ILD for F L0 U1, L0 U1 is obtained by three statements. First one is multiplying the ordinate of ILD, multiplying the ordinate of ILD for shear in the panel L0 L1 by secant theta. Shear in the panel L0 L1 by secant theta. That means shear in the panel, what it is, you must have an idea. That's why I told you earlier, panel shear, some questions we can manage without knowing, but this type of questions you cannot manage. You must know what is a panel shear. Second point is dividing the ordinate of ILD, dividing the ordinate of ILD for moment at L1. For moment at L1 by L0 L1 into cos theta. Next, third one, dividing the ordinate of ILD for moment at L1 by U1 L1. Okay. Truss also they have given. The truss I will show directly here itself. Otherwise, we will show here. L0, L1, L2, L3, L4. This is U1, U2, U3. This angle of inclination is theta. This is the problem. This problem tells you how many ways we can get the same ILD, like you can use sigma y0, sigma m0 about one point or some other point. So, but all will give you same result only. So, let us see how to get this one solution. Now, here I will write one by one. First method. This is again I will redraw this one, the truss. I will shorten this one for the sake of clarity. This diagram we don't require at all. Okay. Like this it is given. L0, L1, L2, L3, L4. This is U1, U2, U3. This angle is theta. Whatever may be the problem, our process is same. Now first we will find the reactions V1, V2. Some reactions are there, let us say. Now we wanted ILD for L0, U1. What is the process? You have to cut it by 1, 1. Load is somewhere here. LHS of 1, 1. Then if this is upward, it has to be downward. F L0 U1. We can find sigma y0, LHS of 1, 1. That is first method. Equilibrium of LHS of 1, 1. Apply sigma y is equal to 0. Upward force is positive, downward force is negative. So plus V1 minus F L0 U1 cos theta. Sin theta we should not write because theta is with respect to vertical. So L0 U1 cos theta you will get the vertical component. Must be 0. So F L0 U1 is nothing but V1 by cos theta. How to read V1? I told you about the panel shear. First panel, second, third, fourth panel. In the first panel, if you want to find panel shear force, stand on the panel, look one side. Unbalanced vertical force is the panel shear force. Such panel shear force is resisted by the diagonal members only. So cut left side, upward force is the unbalanced vertical force. So V1 I will read it as panel shear force. So panel shear force in the first panel, or I can read panel shear force in the panel L0 L1, or panel shear in the panel L0 U1. Anyway you can name it. So I will read V1 as shear in the panel L0 L1. This one, shear in the panel L0 L1. So I can write it as shear in the panel L0 L1 into secant theta. Shear in the panel L0 L1 into 1 by cos theta means secant theta. This is for F L0 U1. If I want to draw ILD, ILD for F L0 U1 is nothing but ILD for shear in the panel, shear in the panel L0 L1 into secant theta. If I want to find ILD ordinate, then ILD ordinate for shear in the panel L0 L1 into secant theta. See the first statement, multiplying the ordinate of ILD for shear in the panel L0, L1, that means V1 by secant theta. So you got V1 by secant, V1 into secant theta. So first statement is correct. Next, I can also take moments of all forces. Second method, you take again LHS of 1, 1, replace FL0U1 by its components, at L0. If you replace it by its components, what are the components? It has a vertical component, it has a horizontal component. Vertical component is FL0U1 cos theta. This is FL0U1 sin theta. This is sin theta because theta is with respect to vertical. Now I can use sigma m0 also. Moments of all forces about L1 is equal to 0. Who knows, I didn't get the idea of sigma by 0, I want to use sigma m0 say. Still acceptable only. So plus V1 into L0 L1 minus, this will give 0 moment about L1, only this will give, minus f L0 U1 cos theta into perpendicular distance is L0 L1, must be 0. See, if I write, if L0 U1 is equal to V1 into L0 L1 by L0 L1 into cos theta. If L0 L1 L0 L1 cancels out, V1 by cos theta, same as V1 by cos theta. That means whether you use sigma by 0 or sigma by 0, ILD expressions are always same. But only thing is the reading is different. So V1 into L0 L1 is, if at all you assume that it is a beam, V1 into L0 L1 is like a moment of V1 about L1. So this I can write it as beam moment, we call it, or simply moment at L1 by L0 L1 into cos theta. But if I want ILD for FL0U1, ILD for FL0U1 is equal to ILD for moment at L1 divided by L0 L1 into cos theta. So second expression, let us see. Dividing the ordinate of ILD for moment at L1, ILD for moment at L1 by L0 L1 cos theta, L0 L1 cos theta. So second expression is also correct. Next, third method. Now why should I replace at L0? This FL0U1 can be replaced anywhere along its line of action from the principle of transmissibility. That also I told you, principle of transmissibility. You must know about the principle of transmissibility. The external effect of a force will remain same wherever you replace along its line of action. So first cut here, throw this piece out. This wherever I want I can keep it. I'll pluck it, keep it somewhere in air here. So if I replace it at this point, FL0U1 cos theta, this is FL0U1 sin theta. If you don't want here, you can replace here also. Wherever you replace it along its line of action by its components or the force itself, external effect is same. So we'll do that part. Replace FL0U1 by its components at U1. How can you replace? From the principle of transmissibility. Now if I write moments of all forces about again L1 is equal to 0. clockwise positive, anti-clockwise negative. So plus V1 into L0 L1, this is over. Now this force I kept it here. What's the advantage of that is L0 U1 cos theta will give 0 moment. Only this will give moment L0 U1 sin theta minus F L0 U1 sin theta into perpendicular distance is U1 L1 is equal to 0. So you will get F L0 U1 is equal to V1 into L0 L1 by U1 L1 sin theta. This is like ILD for moment at L1 by U1 L1 sin theta. See here third one. I dividing the ordinate of ILD for moment at L1 by U1 L1, that sin theta is missing. That means third statement is wrong. So only 1 and 2 are correct. Like that. This is in out of for the past 20 years if you see the questions. Only one of the civil services they asked a question, this one, which requires you should know about the concept of panel shear, concept of principle of transmissibility, how to find the forces. So complete information they asked. But otherwise all other papers very simple, within 1 minute we can complete. This also can be completed, but because I have to explain to you what is the principle of transmissibility, panel shear, we extended so much. But otherwise you can finish off in 1.5 minute time itself. Okay. So this is about the trusses. Now, fifth topic we'll see influence line diagrams for the indeterminate structures. In the indeterminate structures, we will take propped cantilevers, fixed beams, continuous beams, and frames. We take the help of Muller's principle there to finish off the problems quickly because they expect only that. Entire expression they will not ask us. Now, fifth topic influence line diagrams for indeterminate structures. In this first one, we will see the propped cantilever beams. First one in this again, draw ILD for prop reaction. for the propped cantilever shown in figure. Now assume that you are given, say like this. This is a propped cantilever A, B. For VB, we want to show when the load is moving from one end to the other end, how the reaction VB gets influenced. If you draw that influence as a graph, we call it as influence line diagram. So, what we do is we take some general position. First, strength of materials will take it. Then, how to simplify, we'll see. When unit load is somewhere here at a distance of x, L minus x, we know how to find VB. VB will get in terms of x. For different values of x, you plot it. That is what is the analysis. So, we will find VB first, then you draw the curve. Now, to find VB, what you have done? That is the deflected shape of the beam. From the compatibility condition, what the compatibility means? A relationship between the deformations to maintain the continuity of the structure. So, from that it will tell that deflection at B is 0. So, first we will assume that VB is not there. Due to 1 alone, what is the downward deflection? Now 1 you remove. Due to VB alone, what is upward deflection? Net deflection has to be 0. Then from that compatibility condition, you will get the reaction VB. This is what is the process. From the compatibility condition, find VB. Find VB in terms of x for different values of x. Draw ILD. Draw influence line diagram for VB. Now, this is what then compatibility means. We will write compatibility. Compatibility means a relationship between deformations to maintain the continuity of the structure. Maintain continuity of the structure means as long as the beam is resting on the support, it's not slipping and falling down. As long as that is not happening, net deflection at B, deflection in the beam, the deflection in the support, they have to be same level. So, net deflection at B must be 0. Downward deflection due to unit load, upward deflection in the beam again due to VB, they must be equal so that net deflection will be 0. So, net deflection is 0 is a relationship between the deformations. So, that is called compatibility condition. Now, you see how to find that. Downward deflection at B due to unit load. This we know. How we find is if VB is not there due to U load alone, under the load what is the deflection? WL cubed by 3EI. Now W is 1, L is X. So 1 into X cubed by 3EI plus theta into L minus X. One curve then straight line. So deflection under the load plus theta into the remaining length. I think SM sir might have told you deflections many times. So under the load, what the deflection is? 1 into x cube by 3EI. Under the load, the slope is WL square. That means the 1 into x square by 2EI into L minus x. This is like this. Unit load is here. This is x, L minus x. Up to here there is a curve. And from here there is a straight line. So this deflection is W L cube by 3EI. Then here theta. Theta is so much. This distance is theta into L minus x. So this plus this. Theta we know. W L square by 2EI. Like this. This is what you have studied in strength of materials. I am doing it in the same way. So you will get x cube by 3EI plus x square into L minus x by 2EI. This is a downward deflection. Then upward deflection. Upward deflection due to VB. We know this one VB into L cube by 3EI. This is upward deflection. This is downward deflection. Then net deflection is 0. So we can write it as VB into L cube by 3EI minus x cube by 3EI plus x square into L minus x by 2EI. Or if you further simplify, you will get how much? 6EI common. 6 means 3 into 2. 2x cube plus 2, 3. 3x square into L minus x by 6EI. This will simplified form we will write. So this we can write it as how much? Minus 3x cube means minus x cube plus 3x square L by 6EI. So minus, this is the formula, minus x cube plus 3x square L by 6EI should be equal to 0. So from this you will get VB, again common factor if you take it, 2. This push it to the right side. Then minus goes to the right side means you will get minus x cube plus 3x square L. Cancels out, 2 will remain. L cube goes down like this. So this is a general expression for VB. Now the reaction at B has a cubic term, x power 3 we have. So that means you must draw a third degree curve. Cubic curve means simply y is equal to x cube is there, say. That is called cubic curve. Third degree curve or third degree parabola means that x cube, x square, x, all terms can be there. It is a third degree polynomial or third degree parabola. So that means that for indeterminate structures like propped cantilever, fixed beam, continuous beam, anything, for the beams and frames, ILD for reaction is a third degree curve. When a unit load is moving, the deflection has a third degree curve. Okay. So now if different values of x, at x is equal to 0, VB how much? 0, 0 means 0 you will get. Now at x is equal to L, VB value will get minus L cube plus 3 into L square into L by 2L cube. So you will get 1. So draw ILD as shown in figure. This is how the influence line diagram goes. Now see, here it is 1, ordinate is 1, here it is 0, and slope also should be 0. Like this it will run. How to find that this one? You differentiate it, say dy by dx. Then here 3x square, this is 6xl by 2l, 6xl. At x is equal to 0, dy by dx is also 0. That means slope has to be 0. So with 0 slope, draw third degree curve. So this is VB, let us say, ILD for VB. Now this is the ordinate. If you want to find the ordinate here, this is y value is equal to minus x cube plus 3x square L by 2 L cube. This is at a distance of x. At a distance x, y is so much. So it is a third degree parabola, or third degree curve. Cubic curve, if you use that word, simply y is equal to x cube is there, say, then cubic curve. But it is a third degree parabola. Now, your observations are like this. If we have a statically determinate structure, removing the support or cutting the beam or assuming an imaginary hinge will make the structure unstable. Then when you give displacement, it undergoes rigid body, rotation or translation. So you got all of them are straight lines. In indeterminate structures like propped cantilever, remove the support VB will not make the structure unstable. It becomes like a cantilever stable determinate beam. But when you give unit displacement, it will not go a rigid body translation. It will bend like a cantilever. So that cantilever deflected shape is the influence line diagram. So you get a third degree curve. Okay, that's the reason why you got a third degree curve here, because it didn't become unstable. Removing the reaction will not make it unstable. But if you simply supported beam, remove the supports, it will fall down. Now if you lift it as a rigid body, it will go up. Okay, that is first observation. For indeterminate structures like beams and frames, ILD for reaction, shear force, bending moment, all of them are third degree curves. Whereas determinate structure is a first degree curve. And this one, the Muller's principle, also now we can apply here. To draw ILD, the qualitative diagram, how the shape looks like, you can get it from Muller's principle. Remove the support, hold it, lift it by 1. Then the deflected shape of the beam itself is the ILD for VB. Then what is the deflected shape? Muller will not tell you. Muller will tell you only that the deflected shape of the beam. Then the deflected shape is third degree curve or fourth degree curve. You have to take it from strength of materials only. What type of curve, what is ordinate, you have to go for the elastic analysis. Muller simply tells you that the deflected shape gives the ILD. How the deflected shape is given by that? Then that is what he takes it from the proof of that comes from the Bette's reciprocal work theorem. Reciprocal work theorem tells two systems of forces. We will see that reciprocal work theorem, how we apply. Sir might have told you what is the reciprocal work theorem. That from the reciprocal, Bette's reciprocal work theorem, this is derived. That means the reciprocal work theorem, Bette's reciprocal theorem, is applicable to linear elastic structures, which means that your Muller's principle, that deflected shape of the beam gives you the ILD for reaction, is valid only for statically determinate or indeterminate structures, but they must be linearly elastic structures. Only then you can apply Bette's theorem. Then that means Muller's principle also applicable to only such structures. Okay. Now we'll write those observations. These are the points. For statically determinate structures, influence line diagram for reaction. For stress functions, you can say. For stress functions like reaction, shear force, and bending moment are straight lines. For determinate structures, ILD for deflection is not a first degree straight line, it is again third degree curve. Stress functions only, reaction, shear force, bending moment only straight lines. For a cantilever beam, if I want to draw ILD for deflection, we can draw ILD for deflection also. Any quantity you take, you can draw. Then you will get a third degree curve for that. Because for due to point load, deflection is a third degree curve. So ILD is also third degree curve. But whereas for the stress functions, reaction, shear force, bending moment, they are straight lines. But for indeterminate beams and frames, only, not for arches. Arches will get a fourth degree curve because of the expression for the horizontal thrust. But for indeterminate beams and frames, influence line diagrams for shear force, bending moment, for reaction, shear force, and bending moment are third degree curves. Now, second observation is from Muller. How to get it? From Muller. To draw ILD for reaction at any support, remove the support and apply unit displacement. Deflected shape of the beam itself is the ILD for reaction. ILD for reaction at that support. Now, applicability, if I take it, Muller-Breslau's principle is applicable to statically determinate and indeterminate structures. Which are linearly elastic. Why? Because Muller's principle is based on Betti's reciprocal work theorem. Betti's theorem is applicable to linear elastic structures only. So, Muller's principle is also applicable to linear elastic structures, but they can be determinate or indeterminate. So, qualitatively, you will know what is the shape of the influence line diagram. But if you want to know the ordinate also, then you have to take your elastic analysis. That means either moment distribution method or slope deflection method or compatibility condition. Any one method that you have learned in strength of materials, that you have to use it and find the ordinate. But how the shape looks like can be found from Muller's principle. Okay. So this is about the indeterminate structure, how the uh, equation goes. Now see, Betti's theorem. From Betti's theorem, how to get it? Brief explanation regarding the Betti's theorem. Assume that you have our propped cantilever beam will take it. This is the reaction VB. There is a load W. Let us say this then. Now you have a cantilever beam subjected to two systems of forces W and VB. Its deflection profile is like this. This you call it as P system of forces. Now take another system of forces where only VB is there. Now this displacement, let us say 1. This is say some y. This is Q system of forces where in this Q system of forces only VB is acting. Now what is the Betti's theorem? Work done by P system of forces then the displacements must be taken from Q system. Reciprocal means that. So take the P system of forces and take the deflections in the Q system of forces. W is the P system of forces, deflection in the Q system. So W into Y plus VB is in the P system, here it is 1 plus VB into 1. This is W downward, Y upward. So this is negative work done, this is a positive work. That's the work done by P system of forces. Then work done by Q system of forces. VB is the Q system of force. Correspondingly here deflection is 0. So VB into 0. So like that. That is the reciprocal work theorem. Work done by P system of forces must be equal to work done by Q system of forces. So work done by P system of forces, which work done? Not this work done, W into displacement, W into displacement of the other structure. So W downward, Y upward. So minus W into Y VB upward, displacement is also upward. VB into 1. This is work done by P system plus Q system is this one plus VB is upward. What's the displacement here in the P system? 0. Only one force is there. This is work done by Q system. Work done by P, like this. P system must be equal to work done by Q system. So what happens here? VB, you will get W into Y. If W becomes 1, then this becomes influence line diagram. If W is equal to 1, VB is equal to Y. Wherever W is there, corresponding this displacement will give you the VB. So VB is now nothing but the deflection. So if that's why we take only unit load, so that the deflection profile itself will give us the influence of that load. If at all 1 is not there, 10 kilonewton is there, then 10 into this influence, like that. W is there, W into influence. So this is applicable only for the linear elastic structures. From this Muller's derived the formula. So that is also applicable to linear elastic structures. Okay, next. Now, in this problem, you want to find the area of the influence line diagram, say. Next question. In the above problem, area of influence line diagram of prop reaction. Now, if you want to find this area, this is the influence line diagram. This height is 1, third degree curve it is. What we do is we will take to find the area. This is x, this is dx, and this is y, minus x cube plus 3x square L by 2L cube. So integrate it between the limits 0 to L. This length, total length is L. So area of ILD, if you want, total area, integral of y dx. So dx range is 0 to L. I can take dx here, then x is 0. I can take this strip here, then x becomes L. So I can slide the strip between 0 to L. So that's why range is 0 to L. So 0 to L, y means minus x cube plus 3x square L by 2L cube into dx. So you will get say around 3L by 8. This is the answer. But in the exam, if you want to proceed like this, you must know this formula also. To avoid that, you have a second formula, second method. This comes from strength of materials. What we know from strength of materials is if you have a propped cantilever subjected to UD, indirectly we'll find the area. This UDL, let us say W kilonewtons per meter, AB. For this reaction also we know 3WL by 8. Now the influence line diagram is like this. This ordinate is 1. Now this area we want to find. This is ILD for VB. In all the earlier problems, we know the area, we know the load, we don't know the reaction. So intensity into area of ILD is the reaction. Whether it is a point load or UDL, UDL means infinite number of point loads. So infinite number of point loads means I can write it as intensity into area. So intensity into area is equal to reaction. In this problem, we don't know the area, but we know the result. So from that we can get the area. So VB is equal to intensity of UDL, because when UDL is there complete span only, I have to write complete area. If a point load is there, say, then only one ordinate I have to take, but that is not my aim. My aim is to find the area of ILD. So intensity of UDL into area of ILD under UDL. So VB is, we know, 3 WL by 8 into W into area. This area we don't know. So area you will get 3L by 8. This way 5-10 seconds you can complete the problem. But this reaction you must remember. Plastic analysis, strength of material, sir might have told you when due to UDL what is the reaction. Plastic analysis also, again I will derive what is the reaction, how to get this one. Using that we calculate the plastic movement capacities also. So everywhere that 3WL by 8 come, you are expected to remember this basic. How to get that downward UDL is equal to, deflection due to downward load is equal to deflection due to upward load. This 3WL by 8 is not a big deal to remember also. How to get downward deflection, how much? WL to the power of 4 by 8 EI. What is upward deflection? VB into L cube by 3 EI. Net deflection is 0. Net deflection 0 means VB into L cube by 3 EI minus WL to the power of 4 by 8 EI. So even if you had forgotten, to get 3WL by 8 it takes so much time only. But if you have to derive like this and get this value means we didn't study well. Because so many places that 3WL by 8 comes, plastic analysis, strength of materials, structures, everywhere it is coming, so you are expected to remember. So area you will get it like that. Now we will take similarly ILD for VA, let us say. This I remove. Next question is ILD for VA. AB. Now, having understood that Muller's principle we have to apply, we can increase the speed. So, what is the process? Without removing the support at B, Without removing the fixed end moment, there is a fixed end moment also, MA, VA. Unit load may be somewhere here. So, without removing the support at B, moment at A, remove only the reaction, hold it, lift it by 1. Then the deflected shape of the beam itself is the ILD for VA. See here, it is like this. This is 1. Now, see, moment we didn't remove is fixed support. Fixed support slope is 0. So, the deflection profile, this 90 degrees you have to maintain. Now, it will bend like this. This is the deflection profile. If at all support is not there, then this will not be there, then it will go like a straight line, like a cantilever, which we have studied. But instead of cantilever, propped cantilever is there, say. Instead of going up, hold it, pull it down. Then it will deflect like this. That's all. Plus. This is ILD for VA. How we have plotted? Without removing the support at B and fixed end moment and fixed end moment at A, remove the reaction at A and apply unit displacement. Deflected shape of the beam. Deflected shape of the beam is ILD for VA. Now, in case they want, this is what you have to select in 2 minutes time. Indeterminate structure, remove the support, lift it. How it deflects? If you can guess, it takes only 10 seconds time. One of the options is this one. Slightly tougher if you want. If they ask, they can ask you what is this ordinate Y. Now there is a VB. We know this VB is minus x cube plus 3x square L by 2L cube is the VB, third degree curve. Now VA, we know VA plus VB is 1. Supposing that if I take VA plus VB is equal to 1, then what is VA? 1 minus VB. 1 minus VB is minus x cube plus 3x square L by 2L cube. So you will get VA is equal to 2L cube goes this side, x cube minus 3x square L plus 2L cube by 2L cube. You see, VA is also a third degree curve. So general expression Y, if at all they ask you, it is like this. Y is equal to x cube minus 3x square L plus this is general expression for VA. But till now they didn't ask this one. Neither they asked VB also. But we must have some idea of how we have to derive. Okay. If such a big expression is to be remembered, means they will not ask us. But in case if they ask you, this is the process. Now VA is over. I want to draw ILD for say moment at A. Let us say ILD for moment at A means what? Same whatever we have done for the determinate structures. Indeterminate structures also process is same. A, B. Without removing the support at B, support at A, assume an imaginary hinge and apply unit rotation. The deflected shape of the beam itself is the ILD for moment at A. This is ILD for bending moment at A. This is the process. Without removing the supports at A and B, assume an imaginary hinge. Imaginary hinge at A and apply unit rotation. The deflected shape of the beam is ILD for bending moment at A. Now you see how the deflected shape goes. Don't remove the support, don't remove the support. Put a hinge, rotate. Then it will bend like this. Because a roller support, here slope will not be 0, theta b will exist. Some slope will be there, how much it is beyond the scope. We are not interested in finding that value. This theta a is 1. So below reference line it goes. Now this is ILD for moment at A, like this. Now VB we know. One paper they ask like this. This ordinate if I want to find, say, what's the ordinate? What's the bending moment? Bending moment at A for this loading, VB into L minus 1 into X. This I remove. Okay. Note how they can ask is this way. VB is a function of X. What's the function of X means this one? Minus X cube plus 3X square L by 2L cube. Now if they ask you, this is a 2 marks question once they asked, bending moment at A is equal to VB into X, VB into L, which is a function of X minus 1 into X. So ILD ordinate is equal to the function of X into L minus X. One of the options is this one. Otherwise, they have given like this, plus X minus Fx into L. Some convention they followed, clockwise positive, anti-clockwise negative, say. That means not bending moment, simply some moment. Then he will get, this becomes plus, this may become minus. So this is ILD ordinate. Once they ask what is ordinate in terms of a function, f of x. So VB, if you write it as a function of x, f of x into L minus 1 into x is the moment at A, and that is the ordinate, that is the influence for a general expression when you are calculating. Okay. Now this is ILD for bending moment at A. Now I will draw ILD for shear force at any section C. This I remove. This is our last point. This point, some point, let us say C. This is ILD for shear force at C. See here also this is a third degree curve. shear force, Benjamin, reaction, all of them are third degree curves. Now, as I told you earlier, it is also same thing. ILD for simply supported beam, what you have done? Without removing the supports at A and B, cut here. Left portion push it down, right portion lift it up. This is what you have done, minus plus. Straight line. Now it is indeterminate structure, it's not a straight line, completely third degree curve. So total ordinate here is 1. Here also, wherever you want to find it, total ordinate must be 1. Without removing the supports at A and B, cut here. Left portion push it down, then it will go like this. Right portion lift it up, then it will go like this. Okay, this total ordinate is 1 minus plus. How much is this? How much is that beyond the scope? Because big expression, they will not ask us how the shape looks like approximately, they will ask you in the 1 minute time. This is also a third degree curve. Why should it be drawn above and not below? Is convex upward, concave upward? Is that is because the expressions you get like this, hogging, hogging. Both should hog this way. Here slope must be 0. So this is the process. Without removing the supports. Supports at A and B. Cut the beam at C and lift the beam such that total ordinate at C is 1. Deflected at 1 as shown in figure. At 1 enough. Deflected shape. Deflected shape of beam is ILD for shear force at C. Here also slope will not be 90 degrees, some slope will be there. Because there is also a moment, but it is not a fixed end moment. So slope will not be 0, some slope will exist. Here also some slope will be there. It is not like a 0 degrees, 90-degree line will not be maintained. Some slope will be there. Vertical line and this curve, if you drop a tangent, it won't be 90 degrees. From beginning itself, some slope like that will go. Okay. But if it is a fixed support like this, slope has to be 0. Here slope will not be 0. But to that extent, they will not ask you whether slope is 0, with slope, without slope. Two options they will not give you. You have to see out of 4 options, which option has a cut like this. That's all. Ordinate this ordinate expression. What is the slope expression here and here beyond the scope? Because you have to derive, you cannot by heart everything. In the process of deriving, it will take some time. So you supposing that it takes 3 minutes time. 3 minutes is too much of a time in the exam and they will not waste your time. So only qualitatively how the shape looks like they ask you in 2 minutes time. Effectively you have only 1 minute time. That's all. Like that. Okay. Now we will deal with the ILDs for fixed beams, continuous beams, frames. Next we will see that part. Okay, now we'll see the fixed beams case, second one. Same process we will extend. Okay. Now this point, let us say A, B. ILD for VA if you want. Same story without removing the supports and without removing the supported B. Remove only the reaction. Don't remove the fixed end moment. Lift it by 1 like this. Because the fixed support, moment we didn't remove, 90-degree angle should be maintained. Here slope should be 0. So it will go something like this way. Here theta be 0, theta A must also be 0 because they are fixed ends, plus. This is the ILD for VA. VB also same way, reverse it. Then ILD for shear force. That also we can write it. Without removing the supports at A and B, somewhere C is here say. Cut the beam, left portion push it down, right portion lift it up. So that total ordinate again becomes 1 like this. And here the difference is if it is a propped cantilever, it went up like this, now it will go down like this because slope has to be 0 here. So to maintain that 0 slope, a smooth curve can be drawn like this only. Okay, this is negative, positive. For fixed beam, curve goes like this. For propped cantilever, it bulges up, minus, plus, like this. So point of inflection cannot develop there because when the load is moving, point of inflection not possible. So total ordinate here again is 1. This is ILD for shear force at C. Then ILD for bend moment at A. This point let us say A, B. Without removing the support at B and A, assume an imaginary hinge and apply unit rotation. Then like this it will go, but here theta B must be 0, minus. Whereas if it is a propped cantilever, theta B will not be 0, theta B will exist. So I have drawn that's why some slope was there at theta B. Now theta B 0 because it is a fixed support. Now this point theta A must be 1. Then the deflected shape of the beam itself is the ILD for bend moment at A. Only this shape, 4 shapes they give you, this you have to take it. Or shear force means this, VA means like this. This is ILD for bending moment or simply moment at A. In one of the civil services, they asked you to find the ordinate. Supposing that you have say 1, this distance x, this is L minus x. This ordinate I want to find say y. Ordinate of ILD for bending moment at A. This is what you have learned in strength of materials. This is a note. We have a fixed beam subjected to some eccentric load W. This is A, B. Bending moment at A, MA we know W A B square by L square, or this one MB is W A square B by L square. This what moment. Now general expression means general expression for MA we can get, supposing that W becomes 1, A becomes X, B will become L minus X. Then I will get general expression 1 into x into L minus x square by L square. So MA is this much, MA is equal to x into L minus x whole square by L square. Now we see it is a third degree curve, x into x square means. So y value is x into L minus x whole square by L square. Is a 2 marks question that way. So this is ILD for reaction, shear force, bending moment for the fixed beams. Now if they ask you what is the ILD for bending moment at center, ILD for bending moment at center, this point let us say A, B, this is center C, L by 2, L by 2. Now without removing the supports at A and B, assume an imaginary hinge at C and apply and lift it by a distance of L by 8. Then the rotation becomes 1. Then the deflected shape of the beam is the ILD for bending moment at center. Now why should we lift it by L by 8? Again from strength of materials. This is what we have studied. Assume that we have a fixed beam subjected to central point load W, L by 2, L by 2. The fixed end moments here, this is WL by 8, WL by 8. Now if you draw the bending moment diagram, free bending moment diagram is like this value. Then fixed end moment diagram, if you overlap it, it goes like this, minus, plus, minus. Hogging bending moment WL by 8, WL by 8. Total is WL by 4 minus WL by 8. So you will get this also WL by 8. This is your bending moment diagram. Now if at all W becomes 1, supposing that W becomes 1, this will become L by 8. So what we know from this is, due to unit load kept at center, bending moment will be L by 8. That much information we should have an idea. Otherwise simply qualitatively you must hold it and lift it by some distance if you don't know the value. Then the deflected shape of the beam directly gives you the ILD for bending moment at center. 4 options, which option gives you that? Now hold it. Why should we lift it? Why can't we push it down? Because we know that when load is here, bending moment under the point load is positive. So you have to lift it up. If we don't know that, we cannot know should we lift it up or down. So when you lift it, the deflected shape of the beam will go something like this. So this is plus. This ordinate must be L by 8. If I lift it by L by 8, the angle between the tangents, drop a tangent here, drop a tangent here, this theta automatically becomes 1. This is your ILD. One of the options is like this. One get is engineering services, they ask like this. Instead of lifting it, they pushed it down, but they put plus. You lift it up or down, but as long as you are putting the plus sign, no issue at all. This is ILD for bending moment at C. So this is the process. Without removing the supports at A and B, assume an imaginary hinge. Assume an imaginary hinge at C and apply unit rotation. To get unit rotation, hinge must be lifted by L by 8. Then deflected shape of the beam. Then deflected shape of the beam is ILD for bending moment at C, like that. So this is about the fixed beams. They can ask ILD for reaction or shear force or bending moment at support or at center. Any other point they ask, then just lift it. How much you have to lift it, even we don't know. So this curve will not be L by 8, some other value will be there. That's all. Hardly takes 10-15 seconds time to detect. Now we'll see ILD for continuous beams and frames. Now third one is influence line diagrams for continuous beams and frames. Let us see ILD for VA. Now assume that we have this is a frame A, B, C, D, E. Some span is given. ILD for VA we want. So E, C, D, B, we should not lift them. Without removing these supports at E, B, C, D, remove the support and lift it by 1. Then the deflected shape of the beam itself is the ILD for VA. So you lift it by 1. You visualize that ABCD as a cable. When I lift it, it will sag because here is not a fixed support. If it is fixed support, slope also must be 0, then the deflection profile. If it is not fixed, just hold it, lift it, it will sag there itself. Beginning itself, there will exist a slope. How much is that slope beyond the scope? It will become a half an hour problem. So it will sag like this. Say smooth curve, it will go down. Once it is going down here because of support, it has to come here. So to maintain the same slope, it will go up like this. So a smooth curve is drawn. This is positive, negative, positive. Now this is the influence line diagram for VA. ILD for vertical reaction at A. It's a rigid joint. That means angle between the members must remain same even after rotation. Actually, this also rotates like this. but unit load will move on ABCD only, will not move on the column. So no point in writing that when load bridge on the bridges when the vehicles move like this, that's all. When the vehicle is moving on the column, it is not movement of the column, movement of the car, it is the accident of the car. Once it meets with an accident, then only it will go on the column. So accidents we don't deal. So they move like this, forward or backward. Then this is the influence. This if you want to show, you can show how it influences, otherwise not required. Okay. So this influence line diagram tells you that if the load is moving on from A to B, reaction is upward. When the load comes B to C, anywhere load is there, reaction is downward. When the load is here, again reaction is upward, positive reaction. That means if you want to get maximum upward reaction, you must load the span AB and CD. If you want to get maximum downward reaction, you must load on BC only. Such information you will get from this one. Once they ask in a gate problem like this, for the frame shown in figure, to get maximum reaction at A, which of the spans are to be loaded? So AB and CD. That's all. Just draw ILD. That ILD will tell you which spans you have to load it to get maximum upward reaction. So this is the node. To get maximum upward reaction at A, spans AB and CD must be loaded. That is one of the options. To get maximum downward reaction, span BC must be loaded. Like that. Now you see. In the same way, we can draw ILD for anything. ILD for supposing that VD, let us say. We have a continuous beam. Supposing that we have a continuous beam like this. Let's say so much is there. This is A, B, C, D, E, F, G. ILD for VD when you want to draw. What's the process? Without removing the supports at A, B, C, E, F, G, remove the support at D and lift it by 1. Then the deflected shape of the beam itself is the ILD for VD. So, if you lift it by 1, this is the one, let us say. Then how it will deflect is like this. Slope may be 0, may not be 0. Slope will be 0 if they are equal spans. If they are not equal spans, here slope will not be 0. And here if it is 1, say, here may be maximum. We don't know. If the unequal spans are there. Equal spans means we can say that it is like this. It will go up. This is the deflected shape of the beam. If it goes down means it should go up like this. Here also in the same way. Down. It will go down now. Up. Now you see this is minus, plus, this is plus, this is minus, plus. Now this is the influence line diagram. ILD for vertical reaction at D. Okay. which curve it is a third degree curve only, but where is maximum, etc. This is one, but at some other location more than one, whether slope is 0 or not, such minute details we cannot find. It depends on the spans, magnitudes. Okay. So ILD for VD qualitatively from Muller looks like this. From this diagram we can tell that I want to get maximum reaction at D, say. What I have to do? I must load adjacent spans. Leave these spans and alternate spans I load it. You must load adjacent spans and alternate spans. You will get maximum reaction at D. In RCC, sir might have told you, if you have a continuous beam, say, to get maximum reaction at any intermediate support, condition is, your IS 456 also I think might have given, load adjacent spans and alternate spans. So that comes from the influence line diagrams. So this is 2 marks. How we have to load? To get maximum reaction at any intermediate span, at any intermediate support, load adjacent spans, load adjacent spans and alternate spans. 4 options they give you, one of the options is this one, load adjacent spans and alternate spans, like that. How? Don't by heart it, even if you draw the ILD also, then that ILD will tell you how we have to load it. Now if you want to draw ILD for moment at D, let us say, that will go something like this. ILD for bending moment at D is, say like this, you have A, B, C, D, E, F, G. From strength of materials, you have or structures part of it in any continuous beams. At the intermediate support, if loads are kept here, say, then it will hog. So on the adjacent spans, if you load it, then moment at D is negative. At least that much we know. If I apply load here, it will hog. So having understood that point, without removing the supports at A, B, C, D, E, F, G, assume an imaginary hinge at D and apply unit rotation. Not only one span, both spans will rotate. It will go down like this. Once it goes down, here we didn't remove the support, so it will go up, it will go down. Here also you must push it down only, not upward. Because whether load is here or here, bend moment at D is negative. It will only hog. So like this it will go up, then down. This is an imaginary hinge at D. Now you see this is minus, plus, minus, minus, plus, minus. minus. Now you see, if you want to get maximum negative bending moment at D, load adjacent spans and alternate spans. Then you will get maximum negative bending moment at D. Then unit rotation means here you drop a tangent, here also you drop a tangent. This rotation theta is equal to 1. So put together, sum of the rotations put together is 1. So this is your ILD for bending moment at D. How to get it? This is the process. Without removing the supports at A, B, C, D, E, F, G, assume an imaginary hinge at D and apply unit rotation. Deflected shape is ILD for bending moment at D. Now, what 2 marks questions they can ask you is like this. To get maximum hogging bending moment at D, load hogging bending moment at any intermediate support. We can say, we'll write more like this. At any intermediate support, like say D, load adjacent spans and alternate spans. If you want to get maximum positive bending moment at D, you must leave the adjacent spans and load alternate spans. Okay. So if you want to get maximum positive bending moment, you must leave the adjacent spans. These two spans you have to leave them and load the alternate spans. First this one, then alternate spans. To get maximum sagging bending moment at intermediate support, leave adjacent spans and load alternate spans. These are the conditions in RCC also you might have studied. Now we are getting in the, now you have understood the reason why we should load them like that. Okay. Now if we take any frame, let us say this I remove now. ILD for MA. Assume that we have a frame like this. This span, let us say A, B, C. This span is L, L by 2. Now without removing the support at A and C, assume an imaginary hinge and apply unit rotation. That looks like this. Because B is a rigid joint, it will rotate. some rotation. This also to maintain 90 degrees it will rotate, but unit load will not go on the column. So we don't draw this influence line diagram. Here theta B is not equal to 0 because B is not a fixed support. It is a rigid joint. So it rotates. So minus theta is equal to 1. This is ILD for bending moment at D. At A. Process same. Without removing the supports at A, B, C, assume an imaginary hinge at A and apply unit rotation, deflected shape of the beam. So much. Then how to find the ordinates for a frame or a continuous beam? You must take the help of the moment distribution method or slope deflection method. What is that moment distribution or slope deflection is? Again, in the later stages, we will get it. First, you apply load here, say, some load 1. Due to 1, first you will find the fixed end moments. Then you will write the slope deflection equations. MAB is equal to MFAB plus 2 EI by L into 2 theta A plus theta B minus 3 delta by L. Similarly, MBA, MBC, MCB. Then third step, you will find the joint equilibrium equations. MBA plus MBC must be 0. From that joint equilibrium equation, theta B you will get. That theta B you substitute in MAB, you will get the MAB equation in terms of x. For different values of x, if you plot it, you will get a curve like this. Then what is the maximum ordinate, at what distance it happens is a conventional question, 15 marks question. The mains we will see that part. Now prelims part, how the shape looks like and how to get the value they can ask. You must use moment distribution or slope deflection method. That means those methods can be used to find the ILD ordinates in the indeterminate structures. So to find ILD ordinates for continuous beams and frames, we can use moment distribution method or slope deflection method. In one paper, they asked this one, slope deflection method or moment distribution method can be used to find ILD ordinates. Is it correct or wrong? We have to tick it. We can use it for that. We have to use only that only. That is elastic analysis, you have to make it find the ordinate. Then what Muller said was, he gives you only the, you apply your unit rotation, the deflected shape it gives. What is the ordinate? He didn't give. You have to go by taking this analysis. Okay. So this is about statically indeterminate structures, how to draw ILD for reaction, shear force, bending moment for the propped cantilever, fixed beam, continuous beam and frames. Any frame we will have to draw in the same fashion.